What you're looking at is the spreadsheet which I developed to perform the Riffle Run Pool Glide example in HEC-RAS. So as the normal convention is for the spreadsheets, the yellow cells require input from the user. The blue cells are where calculations are done, and the green cells are copied. So you can see the yellow cells have the input data. The overall length is 140 feet. The bottom width of the rectangular channel will be 33 feet. The overall slope, flow rate, Manning's N, and the normal depth, which would have been computed elsewhere. So we take the various percentages of each facet, the riffle being 20%, the glide being 25%, the pool 25%, the run 30%, and the riffle 20%. So if we take the 140 and we get the appropriate length of each one, and then these are the slope ratios which you would then use to compute the bottom slope. So they're based on like 2.5 times 0.006 is 0.015. You would take the length and multiply by the bottom slope and add them together. So remembering that the average bottom slope must be the weighted average of the bottom slopes of each of the facets, you see there's a total change here of 0.84 from one side of the equation and from the other. So it actually balances. Now the slope ratios can be selected based on realistic assumptions about the steepness of the facets related to the steepness of the overall slope, I should say. So you see here the slope of the riffle could be anywhere from 1 to 5 times the overall average slope. Likewise, the same thing for the run. We could probably refine these more, but let's leave them as 1 to 5 right now. And then you see the slope of the pool over the overall average slope might be anywhere from about 0.4 to 0.4. And the slope of the glide might be anywhere from about -5 to -1. So that's basically these slope ratios are a trial and error process. So now you take 10 cross sections, and then you're going to take one section into HEC-RAS and copy it over 9 times. You're going to get the distance between each cross section as being the length of each facet. And then you're going to do the elevation adjustment, which comes from the bottom slopes times the lengths. So let's examine one of these cells. So you can see here, we just take the elevation adjustment and add that to the overall bottom adjustment. That's fairly easy. Let's look at the elevation adjustment. See, it says D12 times F12. D12 times F12. So the length of the facet times the slope of the facet tells you the vertical rise or fall through the facet. So that's how this entire column was calculated. See, the length of each facet is copied over here, and then this is the elevation adjustment is computed, and the overall bottom elevation is also computed. And then you can see, based on the overall distance and the overall bottom elevation, the bottom profile of the channel has been plotted. Here is the riffle. Well, let's start at the upstream end. Riffle, run, pool, glide. Riffle, run, pool, glide, riffle. the downstream boundary condition will be right here. And when the downstream boundary condition depth matches right here, which is also the downstream end of the riffle, then the solution will be obtained. Notice on the right side of the orange line, there is just a complete solution. So if you were playing with this spreadsheet and you happen to type in something by mistake, you can then go back and fix it, but still have access to the correct answers on the right-hand side.